Just to recap, we have gone through 6 chapters already, and for today we are going to go on the last part of chapter 6, which is related to the turbine-based engines, turbojet, as well as turbofan. So we have already looked into the previous 2 weeks to touch into the aspect of the overview or the introduction of turbine-based engine, and we continue to look into the performance parameters of jet engine, as well as last week we cover the turbojet. And then for today we will finish up with the turbofan and having a short conclusion at the end of today's session. So the plan is that we will look into the overview of turbofan. We have already introduced turbofan earlier in our course, and you have been seeing some pictures of turbofan, and basically turbofan engine are the most common engine being used for airliners, especially for the long haul airliners, whether it is a single aisle aircraft or twin aisle aircraft, most of it using a turbofan engine. And then we will look into the historical aspect of turbofan engines, when it was started and how is it evolved throughout the years until the recent years. And we will also touch on the classifications, how turbofan engines being classified, as well as looking into the forward fan unmixed double spool configurations. Before we have a short break, the plan is to have a short break at 6.4.4, and right after the break we will continue on forward fan mixed flow engine, and to end up our session with a forward fan unmixed 3-spool engine. Okay, and we of course we have a short summary at the end of the session today. In terms of the overview, we know already gas generator in both the turbofan as well as the turbojet engines has 3 most important modules, namely the compressor, okay, the combustion chamber, as well as the turbine. Of course, we have the inlet, we have the nozzle, but the gas generator are these 3 main components. In the turbofan engines, the fan pressurizes the air and feeds it aft, and most goes around the engine core, meaning that it is going to be bypassed, it's not going into the core of the engine through a nozzle shaped chamber, and the rest goes through the engine core. I mean, probably around 20% or less will go into the engine core, where it mixes with fuel and ignites. So the hot gases will expand through the turbine section, where the velocity of the air will be further accelerated, and next the hot nozzle as it exits the engine. So there are several advantages to turbofan engines over both the turboprop as well as the turbojet engines. The fan is not as large as the propeller, so to increase the increase of speeds along the blade is less. Thus, turbofan engines power now all civil transport flying at transonic speed up to Mach 0.9, less than Mach 1. Also, by enclosing the fan inside a duct or cowling, the aerodynamics is better controlled. All right, so that's why you can see that there's an engine cowling, where all the fan, the components of the turbofan engine will be sitting inside an enclosure. So there will be less flow separation, especially at the higher speeds, and less trouble with shock developing. If you imagine, if it is just open, you go at a very high speed, there will be a lot of turbulence. So the turbofan may suck in more airflow than a turbojet, and thus generating more thrust because of the diameter of a turbofan is quite significant, quite large compared to a turbojet. Like the turboprop engine, the turbofan normally has low fuel consumption compared with the turbojet. And the turbofan is the best choice for high-speed subsonic commercial airplanes to operate. Right, let us go into the overview, the milestone. What are the historical aspects of turbofan engines? So again, it is we are going to look into summary of the historical aspect in the tables. It is from 1943 until 2016, the recent list that we have in our notes over here. Way back in 1943, right? So manufacturer like Daimler-Benz, you probably heard about Mercedes-Benz. This is where it's all started, right? They are not just building car, but they are also building turbofan engine. Okay, so it is a first running turbofan having bypass ratio of 71%, meaning that what does 71% means? 71% not going into the core, it is being bypassed. Only 29% goes into the engine core. The rest goes around the engine. And then the evolution of the more and more manufacturer getting involved, and Metropolitan Vickers, right? This is a British company, okay? And then Rolls-Royce started to make their way into aerospace, getting involved in gas turbine engine, building turbofan engine, such as being used in major applications in the early stage of Boeing 707, Douglas DC-8 and Vickers VC-10, right? So you can see here bypass ratio of about 25%, right? So, and that is the early Rolls-Royce turbofan engine. And then comes General Electric in 1958, okay, where turbofan derivative of turbojet powered the Convair 990 airliner. We also 1960s General Electric come with a turbofan engine with a ratio of 8:1, powered a Lockheed C-5 Galaxy military transport aircraft. And then comes Pratt and Whitney. So those are Rolls-Royce, GE, Pratt and Whitney are the major players of gas turbine engine manufacturer, right? So 1964, Pratt and Whitney aircraft come into the picture. 1967, RB203 Trent engine. Okay, the engine that being having medium bypass turbofan engine around 10,000 pounds. Right? To continue, I'm not going to go through all of the points here. We have RB2111 type of engine, Honeywell, and then CFM International comes in 1974, Lycoming and Honeywell Aerospace as the manufacturer, and more GE and Rolls-Royce engine being developed throughout the years until 1995. Continue to that, okay, more powerful engine from 1998 onwards, okay, more powerful engines with having not just single spool or double spool, they are also having a triple spool, okay. And we have Virgin Atlantic and other type of modern CFM 56 series of engine come into the market. And following through, April 2010, this is the engine that being used in the FA-18 Super Hornet, okay, also known as the Green Hornet, okay. And then more National Research Council of Canada for Dassault Falcon, the manufacturer, okay, the engine that they produce is General Electric CF700 turbofan. And until the 2016, the LEAP engine, which will be the first commercial engine with CMC ceramic matrix composite turbine. So new material being used for the turbine blades. Okay, so probably if you want to know more detail, you can look into the any propulsion textbook that will tell you more story on the historical aspect of the turbofan engine. But now we want to move into the classifications from the turbofan engine. If you look into this figure 611, it illustrates a very detailed classification of the turbofan engine. I call this as the family of the turbofan engines. It may be classified either based on the fan location, either forward fan or the aft fan. Either it is in front or it is at the back. Okay, and from there, it can be also divided into the number of spools. It can be classified as single, double, or triple spool, as well as going into the aspect of bypass ratio. You can have a high bypass ratio or a low bypass ratio type of engine. The fan may be geared or ungeared, right, into its driving low pressure turbine, and it can be mixed types, low bypass, may be fitted with afterburner or not, and they can also be cross-matching between different categories in this particular aspect. You can see here, it can be mixed fan and core flow, unmixed flow, right? Short duct, long duct. We have the spools here, different variation of the spools, whether they're having geared or ungeared, whether you have a afterburning or non-afterburning type of engine, right? Depend on the depend on the operation, whether the customer, the airline would like to have different maneuverability, long distance, short distance, and so on, the size as well. So it will be considered by looking at the family tree of the turbofan engine. Right. In terms of the classification, we can also define the bypass ratio, okay, known as symbol beta over here, or BPR, bypass ratio. Okay, we have the cold stream of air mass flow rate over the hot stream of air mass flow rate. You can see here, the cold stream of air, basically the bypass air, the cold, or we can say that the mass flow rate through the fan, and then the hot mass flow rate is basically the air, the mass flow rate of the air going into the core of the engine, and that goes into the compressor, going into the combustion chamber and turbine, right? And the cold one is just bypassing, going through the fan, and then meeting the hot gases at the nozzle, behind the nozzle, they mix it again. So what will happen is that if the air mass through the core of the compressor, m dot A, right, then the bypass air fan duct mass flow rate is beta m dot A, okay, beta times m dot A. So the typical component efficiencies and specific heat ratios for a supersonic turbofan engine having a bypass ratio beta equal to 2.7 are given in the following table, table 6.2. So in this particular table, component efficiencies for the engine as well as the specific ratio for moderate bypass ratio, beta equal to 2.7. So we have the modules such as the intake, diffuser. We have the efficiency is around 0.97. For Mach number less than 1. For Mach number more than 1, the efficiency of the intake is 0.885. So this is where we use the specific heat ratio gamma to be 1.4, ideal gas, right? Before it goes into the other component. This is normal value that being used for air at a certain temperature, okay? And then we have the fan component. Normally it is 0.85. So you can see there the different specific heat ratio being used. It's a 1.39. And then at the compressor, efficiency is the same, less specific heat ratio because the air already being heated, okay, because it is being compressed. And at the turbine, okay, you can see lesser specific heat ratio, 1.33, right? And the core nozzle 1.36 and the fan nozzle 1.39 before it goes back to the ambient, before it goes back to the atmospheric, which is already 1.4 specific heat ratio. Okay, as you can see here, these are estimation of the efficiency, and normally, of course, ideally you want it all to be 1. Okay, let us go into 6.4.4, the forward fan unmixed double spool configurations. So the main components here, right, for forward fan, again, you can see back what is forward fan. We have forward fan, the aft fan in the classification just now, and then it is unmixed. There is another category, mixed hot and cold flow, and then we also having double spool. It's not single, it's not triple. This is a configuration of double spool. So in this particular case, we have the intake, the fan nozzle, low pressure compressor, known as also as the booster. We also have the high pressure compressor, combustion chamber, high pressure turbine, low pressure turbine, and the turbine nozzle. So two cases are seen for the low pressure spool, namely the fan and the low pressure compressor. Low pressure compressor, we will use this acronym LPC, okay, and on one shaft and driven by low pressure turbine. Of course, we know already low pressure compressor will be connected to the low pressure turbine, LPT, right? And the fan driven by the LPT. So the LPT is also connected to the fan, and the compressor will be driven by the high pressure turbine. So low pressure turbine connected to the low pressure compressor, and also driving the fan blades. Okay. Meanwhile, the high pressure turbine will be connected to the high pressure compressor over here. Okay. So a schematic diagram for the first type as well as its TS diagram is shown in figure 612 and 613, which we are going to look into in our following slides. And low pressure spool is rotating with N1 speed because it is rotating at different speed than the high pressure spool, right? So the low pressure spool for the compressor and the turbine as well as the fan are rotating at one particular speed, which is lower than the high pressure spool speed, okay, and 2. So in terms of the layout of a double spool where fan and low pressure compressor driven by the low pressure turbine, right? So this is the ambient condition schematic just for the half of the engine. So imagine the air coming into the engine inlet, right? Only a few percent of the air will go into the core, which goes into the compressor, right? We have the compressor stages, right? Over here, the fan, and then we have the compressor, and then we have the low pressure compressor, high pressure compressor. The number 4 going into the combustion chamber, right? Before and after combustion chamber, and we have the high pressure turbine and then low pressure turbine before it goes into the nozzle exit and goes into the atmospheric condition again. So for the flow for the cold air, it will go to the fan, and then it is being bypassed and then going free into the jet, right? Into the jet for that. Then it will be mixed. In this case, it is unmixed, so it is not going back. It is separated between this cold air and this hot air. In terms of the TS diagram, for double spool turbofan engine, which is forward fan unmixed double spool turbofan engine, okay, you can see it is not as a typical TS diagram for a turbojet engine. So that's where we can see here, right, all the pressure locations, pressure locations at pressure at different location. We have the temperature and the entropy values. Okay. Let us look into the analysis. Here we have analysis for different modules of the engine. We will look into one by one. We have the intake. The inlet module is analyzed quite similar to turbojet engine, right? So because it is nothing different, so we can use back equation 6.1, 6.2, and 6.3. So you may want to refer back to our notes last week to refer back equation 6.1, 6.2, 6.3. And with regard to the fan, okay, so turbojet engine doesn't have a fan, so now it is slightly different. Okay, a similar analysis to the compressor section is followed, right? We can follow the analysis like the compressor section using the appropriate equation, but bear in mind the numbering are already different. And this is at the fan, P10, and then P02 times pi F. This is equation 643, and the temperature at 10, station 10 at the fan equal to this expression, which will be used as 6.44 equation. With regard to the low pressure compressor, right, if you look here for the fan and the compressor, we are using the same approach. So now we are sitting at the compressor P03, and we need also to use this expression to find T03. So just to recap back, okay, you can always refer to this station number, A2, 3, and then this is the fan area 10, and then goes into 4, 5, 6, 7, 8, 9, right? So always if you forgot which station, so you can refer back to the figure of the schematic of the turbofan. Right. And then for the high pressure compressor, now we are already reaching station 04, right? So the high pressure ratio developed by the high pressure compressor normally around 10. Okay, so you can use this expression 647 to find PO4 and 648 to find TO4. With regard to the combustion chamber, right, the pressure at the outlet of the combustion chamber is obtained from the pressure drop in the combustion chamber. Okay, so that's where P05 equal to PO4 minus the delta P combustion chamber, right? The change in the pressure in the combustion chamber. Or you can also use expression 649B, right, to find P05. The temperature at the outlet of the combustion chamber is also the maximum temperature in the engine, and already known in advance, because depending on the type of combustion chamber, depending on the amount of heat being used for the Q, okay, QHV, high heating value for the fuel, so you will know the maximum temperature, okay, of the combustion. So thus the fuel to air ratio is calculated in this relationship, where we have zeta B there, the efficiency of the burner, right, or the combustion chamber. We are now going into high pressure turbine, HPT, to calculate the temperature and pressure at the outlet of the high pressure turbine and energy balance between the high pressure compressor HPC and high pressure turbine HPT is performed, right? So you can find using this expression, right, for 6.51A and the ratio, okay, between TO6 and TO5 from this expression, okay, 651B. Here, also the mechanical efficiency, okay, for high pressure spool, right, zeta M1, right, M stand for mechanical, okay, and the portion of the energy extracted by the HPC from that developed in the high pressure turbine is known as lambda 1, okay. From the above relation, the temperature and the at the outlet of the turbine, which is T06, can be calculated, right? So you can find T06 from above the previous equation, and from the known isotropic efficiency for high pressure turbine, the zeta HPT, the outlet pressure from the high pressure turbine P06 can be calculated over here. All right. Now we move into the low pressure turbine. Okay, using the energy balance approach between the fan and the low pressure compressor. Remember, if you I mentioned earlier that it is connected via a shaft. The low pressure turbine LPT, the fan blade, and the low pressure compressor LPC, right? From one side, and the low pressure turbine LPT on the other side. So it is using energy balance approach. So you can have this equation 653A. You have the information of the bypass ratio beta over there. Or another expression can be used to find T07. The pressure at the outlet is obtained from this relation, P07. So you can find the pressure of the at the outlet. We have to note that the bleed from high pressure compressor, and this bleed being used, bleed of air being used to be supplied to the high pressure turbine for cooling purposes. Okay, and also this bleed of cold air being supplied to other accessories in the aircraft. Now, if there is an air bleed, right, from not all the air that goes into the compressor will be going into the combustion chamber. Some of it will be used for other purposes. From the high pressure compressor at a station where the pressure is P03B, okay, and the energy balance with the high pressure turbine gives this. So this is a long expression. That's why we have it equal to the bottom here. So this will be expression 651C, where the symbol B there, right, which is equal to the air bleed ratio. Okay, B means bleed, right? Mass flow rate for the bleed air over the mass flow rate of the air, main air going into the core of the engine, right? Moreover, such a bleed has its impact on the energy balance of the low pressure spool, as the air passing through the low pressure turbine is now reduced. The low pressure turbine getting less air because there are air bleeds because not all the amount of mass flow rate going through the low pressure compressor will reach low pressure turbine because it's already being bypassed and it get being channeled to other places. The flow in the jet pipe is frequently associated with a pressure drop, mainly due to skin friction. Okay, thus the pressure upstream of the turbine nozzle is slightly less than the outlet pressure from the turbine. And the temperature, however, is the same. Okay, so thus you can also equate here where the temperature at T8 and T7 will be the same. However, for the pressure, P08 equal to P07 times 1 minus the change in pressure in the jet pipe. Okay. Moving into the turbine nozzle, so the exhaust velocity of both the hot gases from the turbine nozzle are obtained after checks for choking. And we want to know whether the nozzle is choked or unchoked. Thus, if the isentropic efficiency of the turbine nozzle is zeta and T, right? This is isentropic efficiency for the turbine nozzle, nozzle turbine over there. Then the critical pressure is calculated in this relation, right? Okay, we have that. And for turbine nozzle, when the condition is ideal, where zeta and T equal to 1, then the above equation is reduced. The earlier expression can be reduced over here. But in the case of the nozzle is choked, okay, when the nozzle is choked, the PC is greater than PA, the temperature and the pressure of the gases leaving the nozzle are the critical values. T9 equal to TC and P9 equal to the PC. So you can have the temperature from this relation. In the case of the gas leave the nozzle at speed equal to the sonic speed, and V9 equal to the square root of the specific ratio of hot times the gas constant R times the temperature at station 9, you get the velocity exiting the turbine nozzle. So if the nozzle is unchoked, right, P9 equal to PA atmospheric, then the speed of the gas leaving the nozzle is given by a lengthy expression over here. V9 will be different. Okay, so you have to put in your mind that depending whether the nozzle is choked or unchoked, you will have a different velocity exiting the nozzle. The pressure ratio in the nozzle is obtained from the relation, okay, P08 over PA, and you can have all the parameters that we have obtained earlier, okay. And with regard to the fan nozzle, okay, we have two nozzle. One is at the turbine nozzle, the other one is at the fan nozzle, because this is for the cold air. The critical pressure is calculated from the relation, right, from P10 to with regard to PC, critical pressure. Also for ideal nozzle, zeta Fn, the fan, equal to 1, and the above equation will be reduced to this expression. If it is the fan nozzle is choked, okay, PC is greater than PA, the temperature and the pressure of air leaving the nozzle are equal to T11. Okay, the critical T11 equal to T critical and P11 equal to P critical. The temperature is then obtained from this relationship. Okay, then the gas leave the nozzle at speed equal to the sonic speed. Okay, so we have the cold velocity is V11. In the case of the nozzle is unchoked, you can you know already P11 equal to the atmospheric pressure. So then the speed of the gases leaving the nozzle is now given by expression 656b. Okay. The thrust force, how to find the thrust force from the fan nozzle? It can be obtained from the general relation. So you have a very lengthy expression over here. Okay, you have a V9, we have V11, we have the bypass ratio value, the velocity, we have the mass flow rate of air. Okay, we have the area at the fan nozzle, we have the area at the area 9, okay, and you can re-express it and put all the numbers. You will get the thrust force from the cool air. The thrust, the specific thrust, okay, the thrust force per total air mass flow rate, okay, m dot at, is further evaluated. Okay, total mass flow rate, you can get 6.57b expression, right? And with regard to the thrust specific fuel consumption, TSFC, m dot f over t, okay, you can have that expression, and it is noted from the above equation that the fuel to air ratio, m dot f, is calculated as the ratio between the fuel flow rate and the air flow through the core of the engine, and not the total air flow rate through the engine. We only consider the flow rate through the core. M dot A is the flow rate through the core, not through the fan, and it's not the total, and the total flow rate through the engine. So the thrust force, the specific thrust, and the thrust specific fuel consumptions are calculated over here. Okay, I think it's best for us to have a short break. Probably 10 minutes will be sufficient, okay, before we continue the remaining topics, 645 and 646.